Okay, I think we can get going. Welcome once more. This is the 20th International Tree Mortality Seminar. I'm really happy to see you all here. And it's a great pleasure to introduce Philippe Ciais to you. Philippe, thanks so much for making time. It's really great to have you. And it's really difficult also to introduce you because you've been doing influential work in such a breadth of fields that it's really hard to where to start and where to stop. I will just be very brief. Philippe has a background in physics, actually, has worked quite extensively on the global carbon cycle and carbon budget, has worked for and with the IPCC, has co-authored a vast number of papers. So I think it's more than 1,000. And just in the last year, these publications have garnered more than 30,000 citations in a single year. So Philippe, you're definitely what constitutes a rock star, I guess, in our field here. So it is wonderful to have you. And I am particularly excited because I mean, there's so many things that you could talk about today to us, but you'll be talking about, as illustrated by this nice image, also a very topical subject, specifically harnessing big data and artificial intelligence for forest monitoring. And I think this is monitoring forests and monitoring the changes in forests. This is something that is crucial to a lot of the things that we all do. So I'm really curious to learn about what you're doing and what you're proposing. And before giving the floor to you, I will just also say to the audience that there will be ample time for asking questions. You can do this already during the talk, during Philippe's talk. You can post your questions in the question and answer field, which you find below in your Zoom panel. So post your questions there, and we will then relay your questions to Philippe, and he will answer them after the talk. And with that, Philippe, thanks for being here once more. The floor is yours. I'm looking forward to your talk.
Okay, so thank you very much for the invitation and for the introduction. And I've been working a lot with the process-oriented models. But I find that it's always frustrating because their level of development is always a little bit pathetic compared to the reality we are facing. And that's the reason why, since maybe 2 or 3 years, I've started to look more at the problem of understanding and monitoring forest carbon with data, in particular with satellite data. And it's clear that the kind of societal and climate stakes related to forest are very high. In the global budget, forest alone are estimated to make up most of the land sink, itself absorbing about 30% of the emissions. And the most important thing is that many countries are counting on forests to meet their climate target. So basically, they are counting on their forest sinks or even on improving their forest carbon uptake in order to meet their neutrality goals. This is the case of Europe. Europe wanted to cut their emissions by 40% in 2030 compared to 1990. And they decided 2 years ago to open the Pandora box. Instead of only looking at industrial emissions, they said, okay, let's give us a more ambitious target. We want to cut our emissions by 55% instead of 40%. But this time we will use the land use sector. And in the land use sector, the sink is mainly in the forest sector. So basically, the EU, for instance, as many other countries, are counting on forest carbon uptake to improve their commitments to neutrality. In fact, in Europe, the situation is that we have seen from ground data quite a persistent increase of disturbances. And as you know, in this group, disturbances are a very good example of fast and sometimes massive losses of carbon that can, in one event or a few years, negate the slow carbon accumulation. Exposure to climate risk have increased over the last 40 years. And I take the example of France, for instance. We see that over the last 10 years from the NFI data, the mortality of trees has increased by 80%. I'm talking here about the natural mortality, not the harvest. It was, I think, 4% as a background value, including a few big storms, and now it's about 8%. What is even more worrisome is that many forests are planted, they are not self-regenerated, and we observe a 54% failure of the new plantations. So under this question, the EU has committed to create something, to maintain something in the land use sector. And when they took the decision, if you look at the numbers, basically negative are uptake and positive are sources, basically cropland and emission of greenhouse gases. And if you look at the green curve is the European forest carbon sink as given by national inventories. And it was pretty stable. It was about 450 million tons of CO2. And starting between 2010 and 2015, the sink has gone down substantially by almost 20%. And we are now below the target that was taken by the EU. So when they choose the target, in 2030, we'll have a carbon sink of 400 million tons CO2 per year. It looked easy because the actual uptake was above this number, but the sink has decreased. And this decrease, as I said with the French example, is mainly due to an increase in mortality and the slowdown of tree growth. Some countries, like I think the Czech Republic, if you look at their national inventories, have turned from being a sink to being a source because of massive bark beetle attacks. In France, if you plot the same diagram, the national forest carbon sink has dropped by 40%. So it's 3 times more than the average over the EU. So it's clear that we are facing a problem. And the question is, what data do we have to at least monitor what is going on? We have, of course, forest inventories. They are forming the backbone of the long-term monitoring because in many countries of the north, the plot networks are dense. Inventories have been designed to give an average carbon stock of a nation. They have not been designed to give the average carbon stock of a small region because of the limited amount of plots. It's labor-intensive work, it's accurate tree-level data, and the idea is to make a poll of the forest. For instance, in France, the national inventory is measuring every year 14,000 plots. 7,000 are revisit of plots that were previously visited 5 years ago, and 7,000 are newly chosen plots. So although this is sufficient to have, let's say, an average stock, when the system is changing in a way that you have small regions that can be affected by massive losses, like fires, wind, insect disturbances, the capacity of the sampling of the NFI to detect fast changes, especially when you bring it from the national scale to the regional and to the forest scale, becomes very limited. The second point is that intrinsically, the sampling scheme is a kind of running mean over 5 years. So if you have a shock year, like in 2018, it was a very severe drought in Germany and Poland, you will only discover the impact of the shock when you will have passed your running mean through the shock year. So it means that it's only 4 years after the shock, where you may have lost a lot of carbon, that you will have a better idea of how much carbon has been lost, but you still are not able to account for the instantaneous, let's say, interannual change of carbon in the forest. On the other hand, we have also, eddy covariance measurements. It's a completely different observing system, much more expensive. They do provide very accurate records of the net carbon exchange with the atmosphere. They have some kind of upscaling properties, and a lot of work has been done to use satellite data and climate data to provide gridded estimates, but they remain extensive research-based measurement, and they do not give us information about the carbon stock directly. That's why the existing asset probably needs to be complemented with satellites. And well, I don't need to explain that satellites offer a lot of advantages. The advantage of a global coverage with consistent measurements, the advantage of a relatively frequent revisit, and also they measure different properties that are interesting for looking at carbon. The classical sensors are MODIS. Of course, there is a compromise between spatial and temporal resolution. MODIS flies daily over the globe and has a resolution which is moderate. Landsat has a higher resolution, but it has less frequent images. And what has been a bit of a game changer, and I'll try to find the time to speak more about the use of those data, is that thanks to some Californian innovators, basically companies that have launched micro satellite or cube satellites, we now have the possibility to use constellation of imagers that bring the best of the two worlds. Basically, they provide high spatial resolution down to 3 meters, even better for some of the sensors like worldview. And they have a frequent revisit. So now, thanks to constellations like the Planet Data, we can have an image of the Earth every day at 3-meter resolution. The drawback is that the quality, in particular the spectral quality of the data, is not as good as the one of the research class satellites. So satellites offer a new window to monitor wall-to-wall carbon. That can be like a propaganda thing for a space agency or research agenda. But keep in mind that if we had the satellite that measure forest carbon, we would be in good shape. But none of the observing satellites are giving you a carbon variable. Satellites are measuring colors, spectral colors, radar backscatter, sometimes LiDAR properties. But these physical measurements have to be translated into carbon quantities. And that's what we try to do in collaboration with colleagues from INRA and Copenhagen University, and now working also with Cornelius and his group. We have been trying to make sense of satellite data combined with ground observation to derive maps of biomass, maps of biomass change, and maps of, let's say, activity that can be used to attribute those changes. We are facing a problem is that if you see that there is now an image of the Earth at 3-meter resolution every day, it's plus all the existing other sensors. It's a deluge of data. And the kind of classical way of doing remote sensing, taking one satellite, a couple of bands, forming some spectral indices, is impractical. If you want to make use of all this data, you have to change a bit the kind of model that we are using to go from satellite data to carbon. And that's why machine learning and deep learning offer some advantage. They have also some inconvenience to convert a deluge of satellite data that human brain cannot make sense easily anymore into a carbon quantity. The disadvantage of machine learning method is that they are a bit like black boxes, so they will give you an answer, but they still have some kind of interpretability issues. So to start with, as a good example of what we did without machine learning with Jean-Pierre Vigneron, as you know, monitoring biomass change is still something extremely difficult. And Jean-Pierre had the idea to use basically the noise of other satellite communities to derive an indicator of biomass. The SMOS satellite and the SMAP satellite are L-band passive microwave antenna. They measure the kind of emissivity in a microwave. And usually people don't like vegetation because they use a satellite to retrieve soil moisture. And vegetation contains water, so it's basically an annoying thing for that prevents nice retrieval of soil moisture. But you can see it the other way around. You can say, well, after all, if vegetation water content influences the signal, we should be able to look at the volume of water in the vegetation and to transfer that in biomass. And it is this nice indicator, this vegetation optical depth, which is nicely related to biomass, with much less saturation than any optical or shortwave, microwave data that we used to create this global map of biomass change. You see in the picture in green the areas where we think from this L-band data that over 10 years there is a gain of biomass. You recognize some of your pet sink areas like southern China forest in dark green, also this abandonment of agriculture area in the south of Russia. And you see also brown areas where we have a loss of biomass in the deforestation frontier of Brazil, also in Central Africa. And indeed, visually, the map was kind of nicely correlated with the forest loss map. So with this proxy, we found three things. The first one is that the global biomass stock increase on average over 10 years is only 0.5 gigaton of carbon per year. And we said, well, it's too small because there was this famous Panetal paper which says it should be 2. But then we looked at many other satellite biomass change data, and they all give you a global biomass increment, which is between 0.2 and 0.5. So we have here already an interesting question for the global budget. Maybe the satellite data have some saturation and they are missing some of the global carbon sink. It's possible. Maybe they are right, and then it would mean that the global carbon sink, only 25% of it is in biomass, and the rest is in non-living things like coarse woody debris. It's possible, so organic carbon, sediments, and so on. So VOD is nice. It's one of the first record of 10 years to track biomass change. Of course, it has some issues, but it's at a coarse resolution of 25 kilometers, and it's a bit coarse to understand the processes at play. That is why in a kind of second step, and we are not the only one to do that in the world, we started to see how we could produce better biomass map from JEDI. I don't know if you know JEDI, it's a fantastic instrument. It basically consists of 4 laser beams, which are traveling across the Earth from the space station. And JEDI is sending a beam of infrared photons. So we have 8 orbits, and the beams are like a forest inventory. Basically, it has the size of a forest plot, a diameter of 30 meters, spaced by 60 meters from each other. And the JEDI measures the waveform. The waveform is showing the first return of the photons on the tallest trees in the footprint. Then you have a vertical structure which depends on the position of branches, leaves, and understory trees. So if it has a high peak, it means that it's a kind of monolayer, the top canopy. If it's very flat, it means that it's a kind of very dense and very thick canopy. And it has a ground return. So from the difference between the top height and the ground return, you can get a direct height measurement. And we all know that height is related to volume, is related to carbon. The problem is that JEDI is an incomplete sampling. It's like an NFI, but very much denser. In France, we have 14,000 NFI plot, and there is 100 million footprint of JEDI. But still, the question is, there are still some gaps in between. So what we have been trying to do is to try to teach a deep learning model, which is called a UNet model, to produce continuous high-resolution maps of forest height using as an input data images, which are coming from optical data, so 10 band from Sentinel-2, and radar data for different images a day, every 5 days, from Sentinel-1 radar. So imagine that this problem is simple. Y is a dependent variable, it's a LiDAR height, and X is one band of Sentinel-1, Sentinel-2. So you would write a regression model like Y equal AX plus B, and you find A and B. The problem is that, of course, the relationship between height and spectral indices or radar is highly nonlinear. And what the UNET model, which was derived from medical imagery, is doing is that it's providing a convolution of images where the coefficient of the regression are the weights of the convolution. And typically with a network like this, you have about 17 million of regression coefficients, if you want, trainable weights. It's still not overfitting because you have billions of satellite pixels in the input data, and you have also millions of JEDI footprint. So this is an example. This is a forest that lives in the north of France. It's called Crécy. You have a Google Earth image. And this is what JEDI is showing you, the raw data. Raw data of JEDI shows that there are some regions of this forest which are yellow, so the trees are tall, about 30 meters. Some forests which are very short, but still it's difficult to give an idea of the distribution of height. And after training our UNET model, of course, we verified that there is no overfitting and so on and so forth. You get something which is looks like a nice picture of the forest. You see the geometric variation of height because you have some forests that have been cut and they are recovering and they have different height. But you see in this central forest, which has tall trees, that you have also some kind of disturbance, roads and gaps, which are almost detectable with this high-resolution height map. So we produced a map for France and now for the globe at 10-meter resolution, and using a simple allometric relationship at stand level between height and biomass, we derived a biomass map. As you know, biomass, it does not make any sense to derive it at 10 meters because you spot a trunk, a stem, you have 2,000 tons, you move your pixel 10 meters away, you have a branch and you get 10 tons. So it makes sense only to infer biomass at a spatial scale where you have many trees, or to do it at tree level, which we cannot do obviously with the 10-meter satellite resolution. The question is how good it is. Okay, I produce nice maps. You can see that the Alps and the east of France have a taller forest than the Mediterranean and the Leland plantation. So we did some evaluation using two observing systems, which are completely independent. They are not used in our model. The NFI data, so you see all the NFI plot in green. Some kind of permanent plot called ICP, it's a French ICP, and some airborne LiDAR campaign. And we were pleased to see that after several adjustments, the model was able to predict quite accurately the values of height at the NFI plot, which is on the x-axis, which is completely independent from the model. So it's possible, yes, from spaceborne data, to have a very accurate prediction of height with a mean error of about less than 3 meters. Similar performance for the evaluation against airborne LiDAR data. Still some classical problems of those deep learning models. They tend to underestimate the tallest trees because there is not enough training data. And we said, okay, this is nice, but we are not the only one to do this. And there are other products that produce forest height. First of all, we have a Potapov paper. They used a similar approach with the Landsat instead of Sentinel and JEDI with the random forest. Nico Lang has been using JEDI data with the Sentinel-2 only, and we use Sentinel-1 and 2. And there was a recent paper by our colleagues from Copenhagen. They use the planet data, so it's really the heavy artillery, and the airborne LiDAR to produce a height map at 3-meter resolution for Europe only. So how does our height map compare to other height products? First, a visual inspection. Potapov on the right, Lang, then Liu, this planet product, and our product. They look similar, but not quite. The Potapov map looks very flat. Lang looks very more like fuzzy. I mean, it's not as sharp as our map. And Liu has the same kind of contrast, but it seems to be producing lower height in many parts where we diagnose the tall forest. Which one is right or which one is better? So this is an example of the comparison between the airborne, like the true value, the airborne LiDAR height. Again, the 4 products ranked from right to left. And we found that Potapov and Lang have low correlations with this kind of ALS data. I was surprised because I would have expected that the Planet product would be better than our Sentinel-1 and 2 based product, but indeed, it's the error and the correlation are slightly lower than what we obtained with our deep learning model. Why is our map better for France? Well, maybe because we are French and we designed the model for France, so it's easier to do it than the global product. Maybe because we use the better deep learning model. Maybe compared to Lang, because we injected the Sentinel-1 SAR data. Maybe the Sentinel-1 data are making some difference. And as I said, maybe because our study was local and the other products, at least two of them, were global. Second thing, once you have an accurate height map, you can talk to Cornelius and Rupert, and you can use their disturbance map to look at the height today, or the biomass today, and the age of the forest, which is the time since the last disturbance occurred in that pixel. And by putting these pairs of height or biomass and age together, you can derive what you call a growth curve, which defines the recovery of height as a function of time since disturbance. We did that here for a small region in France. And with the Landsat data, you get all the color curves, which correspond to each species because we cross those recovery curves by a high-resolution species map. Beyond the Landsat era, you cannot estimate a height for forests which are older than 40 years. So we completed them by the black dots, which are the NFI age and height measurement. There are several good news. First of all, these curves are important because they can be used for management and the expectation of recarbonization and so on and so forth. Secondly, you see that there are some clear difference in growth rate between fast-growing species like poplar and slow-growing species like oak or fast-growing species like Douglas. On average, in this region, we did not find any significant difference in the fit parameters with the Chapman-Richard equation between the conifer rate of regrowth and the broadleaf ones. And the third good news is that the satellite-based, so based on our height and the Landsat disturbance map from Cornelius, and the NFI data, they are very consistent with each other. So two different ways to retrieve growth curve give a very different, a very similar result. So once you have growth curve and biomass data, you can use that for a number of applications. One interesting application is that in 22 in France, we experienced a completely incredible year with extreme fires that happened in regions where they do not happen before. Usually in France, fires happen in the south of France, in the Mediterranean biome, with some internal variability. So you have the burnt area at the bottom. And suddenly in 22, because of a very long and dry summer, we had two mega fires in the Leyland forest in the Atlantic part of France, and a few fires in temperate forest. And by crossing our high-resolution biomass map with the Sentinel-2 burnt polygons, we found that this is really an extreme year because the Mediterranean did not lose more biomass than usual, even less than usual, but you have this new fire regime. In particular, those affected some old growth forest in the north of the Leyland plantation that make up a very strong loss of biomass, which is estimated to about 2 tons of carbon. Another interesting result is that we have very few fires in the temperate systems, in Brittany, for instance, or in Jura, but these forests have 2 times more biomass than the Mediterranean forest, and therefore, even though the burnt area was small, the biomass loss was even higher than in the Mediterranean regions because the impact system had a higher biomass density. Then we tried also to look a bit more closely at the map of disturbance because all this loss and regrowth depend on the disturbance agent. And you know that there are different types of disturbances, very different, like you have rare and widespread things like storms, fires. You have also a lot of cuts. Some biotic dieback, just like defoliators, for instance, that we try to distinguish from biotic mortality, which is mainly bark beetles, so insects that defoliate but not kill, and insect that kills. And we tried to provide an attribution of the map of Cornelius by using also deep learning. We use different data sets. We have more than 10,000 field observations of forest health as part of the inventory, but it's not a national inventory. It's just a forest health survey. People go in the field and they say, oh, there is a bark beetle, oh, there is a defoliation, blah, blah, blah. Secondly, we have the NFI. Each 5 years, they give you tree-level data, and they tell you, oh, it's a spruce forest, and there was some natural mortality, or 10% of the trees have been chainsawed. And then we have another database, which is a semantic database called DFDE. It's basically a big Excel spreadsheet where you see, oh, there is fire in the region of Münster in Germany in 21, but there is no geolocation. It's just a text. So if you apply text mining plus, you kind of find some distance between each of the disturbance polygon and the site where you have either health observation or NFI observations. Of course, you know there is a disturbance, but there is a time uncertainty because NFI is only revisited every 5 years. Plus the semantic data, we are trying, it's not perfect yet, to make a classification of the nice disturbance map that was produced from the Landsat data. It's working okay, but it has a lot of margin for improvement. One of the margin for improvement is that we know that the disturbance sometimes don't come alone, like you have a drought, and then you have a bark beetle attack, and then people are obliged to do salvage cutting, and they cut the forest. So what is it? Is it biotic mortality, or is it a cut? If you look at an NFI data, you see the tree chainsawed, and nothing tells you that there were bark beetle before or not. If you look at satellite data, you need to have high frequency to detect a kind of cascade of things that are going wrong. But we have been trying to associate basically consecutive forest disturbances to look at those cascading effects, which is not completely easy, but it's work in progress. We also use the disturbance map and our growth curve derived from satellite data. In this case, we don't use our LiDAR data, but CCI biomass. We noticed that there is an increase of the disturbances, also an increase in their severity in many regions. Here, Europe is divided in few regions. So we divide Europe into small squares of 18 kilometers, in which you have many 30-meter disturbances. And then our postdoc, François Ritter, has been trying to derive growth curve, one every 18 kilometers. So we know how much carbon is regained by the forest after disturbances on a grid. Here I show you only the aggregated regrowth curve, which are derived from satellite data for different regions. So you have the Alpine region, the Boreal, the Atlantic. You can see that different regions differ by their asymptote. Obviously, you can get a much higher asymptotic biomass after full recovery in the Alps or in the continental part of Europe compared to the Mediterranean or the Boreal region. And also the regrowth rate is smaller, slower in the Mediterranean compared to the other regions. How good are those satellite products? Well, we compiled with Nuno Carvalhes a large database of chronosequence of forest plots where you have biomass and age. There is a lot of noise, of course, because the plots include species, soil differences. They are very local measurements, and our curves are a kind of average integrated recovery at 18 by 18 kilometers on a grid. But still, there was no significant bias across all the age bins between our regrowth rate and the one you can get from a few plot data. So then we said, okay, we know the recovery. We still need to know how much biomass is lost for each type of disturbance. And this was not easy because we have a map of disturbance severity, but the world is not simple. It's not because disturbance severity is 0.5 that you lose 50% of your initial biomass, or because it is 1 that you lose 100%. The ratio between the disturbance severity and the biomass lost is not constant. And we had no way to infer it on a grid. So basically, what we did is that we defined this parameter, this ratio of severity to biomass loss, as a single scaling factor per country that we tuned to match the NFI data. So this is our magic tuning. We tune it only 1 year. And the good thing is that our model, which now predicts the development of carbon, because every year you read the disturbance map, you know how much is lost from your magic ratio, and you know how much carbon is regrowing. Our black curve for each region, but we can do that also for each country, is now following relatively well the NFI trend of year-to-year changes of AGB, which is a carbon sink in biomass. That is good, because if you try to do it directly from the CCI map of ESA, they have 3 consecutive maps. If you make a difference from year on year between 2018 and 17, 2019 and 18 between the maps, the ESA map will tell you that Europe is a source of carbon in biomass, which is not true. We have enough NFI data to know that we are still a sink, a decreasing sink, as you can see, but still a sink. We believe that this is because the ESA map is capturing very well the losses, but it has some striping effect, and it has also maybe some problem to capture the growth of forests that have a high biomass. And if it is skewed towards seeing the losses better than the sinks, it makes sense that when you make the year-on-year difference of the biomass from the CCI maps, you are going to overestimate the losses and you get a non-realistic carbon budget. So now we have the calibrated model that gives you gain and losses. The only thing we did is we made the hypothesis that in each region, the trend of disturbance severity can be linearly extrapolated from the last 30 years. In the regions where you have a trend, that's what François did. So he can now calculate on a grid, but this is shown for the broad part of the European forest. He can calculate what will be the biomass carbon accumulation, the net one, including the loss from disturbances, if disturbances have a trend of linearly increase in severity. And the bad news here is that we predict with this very simple data-driven model, extrapolated to the next 10 years, that the European forest sink will continue to drop, and it will drop to a much lower value than the political target of the EU in most of the regions. And indeed, some regions like boreal forest, but also some parts of France and Eastern Europe are going to be net carbon losses, even if there are small declining carbon sinks today. So now, this is what we can do with the model, basically a bookkeeping model with loss and gains. Another interesting approach to monitor carbon gains is to do it directly from the satellite data. But the signal is small. It's easy to detect a height of 20 meters out of 0, but it's very difficult to detect a height increase of maybe 1 meter per year. Its signal to noise ratio is much smaller. So we tried with the UNET model to build basically a year agnostic model. So we have the Sentinel data for 5 years, we have the JEDI data. We don't want to be sensitive to phenology or drought or internal variation. So we teach the model how to model height in a robust way, whatever the darkness or pale color of the vegetation due to drought and phenology. And by building a year agnostic model, we can then use it to predict year-to-year changes of height. This is an example of the model result. So we now have a map of height every year. This is a small plot in Leland. And if you make the difference between the final and the first date, you see a lot of red areas that have lost their height. And this is obviously because they have been clear-cut, as you can see from their geometric forms. What is more interesting is that you have a lot of plots that are green and they have gained height. And the question is that, is this carbon gain or height gain signal realistic or not? Is it, does it make sense or not? Maybe it's just an artifact of the trend of greenness or radar data and the JEDI noise. So indeed, it seems to make sense. When you consider the map in 2018 as a baseline, and you make a difference between the height map you get in 2019, then 2020, and so on, for the forest in Leyland, you see that the trees that are 5 meters tall, they seem to grow quite well, as you would expect, by almost 1 meter per year. But the trees which are 20 meters tall, they grow very slowly. And that makes sense. But it's still interesting to see that using these deep learning models, we seem to be able to calculate a growth signal from year on year, even if it's a very small signal compared to basically having just a height map. This is another type of forest. The one on the left is a pine forest, maritime pine plantation. They grow very quickly, as you can see. The other one is Aleppo pine. It's a completely different species, slow-growing species in the Mediterranean region. And you can see here that the growth rates are, in fact, very slow and that they tend to be higher at taller height, older trees compared to younger trees. And the last curve is the Douglas fir. Douglas fir is a monster species. It's planted over clear-cut in the center of France. And when the plantation closes, you see the trees, the Douglas, which are 10 meters high, they have a crazy high growth rate. And then, of course, the growth rate declines when the trees get a little older. So with this new map of annual height change, we can produce some kind of height on biomass increment at the scale of those relevant management and the climate region of France. So now we said, okay, we have done some work for France. We had some papers where we applied similar models for Ghana, for Tanzania. We are working for Spain. And on the other hand, there is some global product from Nico Lang and Peter Potapov and others. And they seem to have some kind of quality difference. So the question is, why is there a difference between the global product and the local product? And using the same model than the one we deployed for France, we found that if you look at our map for France, for instance, it has much more contrast, and it looks to be of better quality than the global map. So we trained basically a global model with the same kind of technology. And we found that the global model, based on JEDI data and trained by Sentinel-1 and 2, can give a result of the same quality than our kind of super-tuned model for France, which looks much better than the quality of previous global model. The same for the Amazon. It's quite amazing compared to the long map that is very kind of has low contrast. You can almost see group of trees in the Amazon at 10-meter resolution with this new high-resolution map. It has a good cross-validation performance. How do we do that? Well, you just need to have a very good computer equipment, and that's what they have in Münster University. They have also very good skills in machine learning. They divided the world into time zones, and they have basically processed all the Sentinel data. Each snapshot is 45 terabytes of data. The JEDI raw data itself is 30 terabytes of data. When you filter the bad data with clouds and fogs and no height, you get still a 200 gigabyte data set. We use a JEDI UNet model. I pass on the technology, but we are aware of the fact that there are some geolocation error in JEDI. So we use an adaptative loss function. Basically, we move the JEDI granules by a certain error, which is the declared geolocation error of JEDI, about 10 meters. And we pick up the shift of the JEDI footprint that are in best agreement with the data. So this allows us to correct problems like this one. You see that the measurement of JEDI are supposed to be in a forest, but they give you a height of 2 meters. So obviously, they are shifted north in the reality, but the geolocation tells you that they are in the middle of the forest. And using this kind of shiftable data of JEDI, you can partly account for the low correlation geolocation, the high geolocation error of the JEDI data. Okay. And then you just basically need to have a big computer. What is amazing is that maybe 5 years ago, you need a team of 50 people to do that. And now a graduate student, a very smart one, can do the entire training of the deep learning model on 3 GPUs for 2 days. And then it can produce a global map, provided a lot of GPUs, 40 GPUs, in only 2 or 3 days, which means that today, a grad student can produce a global map of forest height or forest biomass at 10-meter spatial resolution in 1 week. And then you can change the parameters, adjust, and so on. We have to validate the map against LiDAR data, but we have, for instance, a product for Congo, if you are interested, and the Amazon of height, not yet biomass. You can see that there is apparently over Congo a very tall forest in the western part of the Congo basin, or the Central African forest, I should say, compared to the eastern part. And when you compare the quality of this height map to the ALS data, there are a lot of ALS data in DRC, in Cameroon, so we did a systematic comparison. You can see that it's not as good as that we get for France, but we still get a mean error of about 4 to 5 meters. And the forests are completely different from European forests, and they have a height of up to 60 meters. And the comparison between the satellite model and the kind of ALS data, you can compare the red curve, which is the ALS, and the green curve, which is the model, is very good. So the model is quite capable to capture the small scale heterogeneity of the forest. I think I'm running out of time, right? So I should maybe conclude. I just wanted maybe to show some of the work in 3 slides that we are doing with our colleagues from Copenhagen. They are doing amazing things with the planet data. They have trained the UNET model to try to do height and tree cover attributor, basically by using as an input the planet tree meter images and trying to ask them to mimic the ALS height over campaign regions. So they produced a very accurate 3-meter tree cover map of Europe and a 30-meter biomass map. This trees outside forest is an interesting topic because in some countries like the UK, we found that 25% of the tree cover is not in forest because it's very bare, it's very fragmented. You have very few big forest chunks, and a large fraction of the canopy cover is in land cover classes that are called cropland, grasslands, or urban trees. And on the Atlantic part of Europe, like Brittany, Netherlands, Denmark, it's about the same story. Using this time even higher resolution data, so we're talking about aerial photos with a resolution of 20 centimeters. It was possible to segment all the trees of Rwanda and here of Denmark using a double task UNET model that does both height and canopy segmentation. This paper you may have seen, same technology using, I think, worldview satellite at 0.5 meters. You ask postdocs or humans to delineate trees, but of course, if they have to do it manually over such a big region, it will take them several decades. And then you train machines to infer the height and the area, and from this, the biomass and the carbon of those arid trees. And we counted about 11 billion of trees from the Red Sea to the Atlantic Ocean. This is an example for Rwanda. Another example, which is very cool, let's say cool or bad news, I don't know. India is the biggest country for agroforestry. It has a huge amount of trees over cropland. And the group of Copenhagen, they make the difference between the large trees. So we are sure that there is no false positive in the detection between the rapid eye satellite images in 2010 and the PlanetScope data, average over 2018-22. And to our surprise in this study, we found that in most of the regions where there is agroforestry in India, you see that many trees, which are indicated by the pink dots, have disappeared over 1 decade. So why do we see a disappearance of large trees over agricultural landscape of India? We try to do some interviews and surveys of local rural communities. We thought it would be due to drought or maybe some disease, but in fact, it's just that people are getting richer. They buy machines to do harvest and they don't like the trees, so they are cutting the trees and they are cutting the large trees, unfortunately. One last thing is that can we do better with high resolution images? And in this new study, we tried to ask a deep learning model to do biomass at plot level. So you take an NFI plot And inside the NFI plot, you have a very high resolution 20 centimeter image. And you ask to a computer to use the texture and the information contained in this very high resolution image to create a single dependent variable, which is the biomass at the plot level. Is it better to do it by trying to segment all the trees, but then you miss the understory trees in dense forest, or just to exploit with the magics of deep learning the texture of the images themselves? And the answer is here. It's quite amazing. You can compare the performance of a brute force segmentation. So you contour every tree, you have the height because you have some LiDAR data. We can get a fair estimate of biomass at plot level with still, a correlation coefficient of about 0.7. That's the best we can get. But by using just the textural information of the airborne images, you can get a coefficient of correlation which is close to 0.9. So there is something contained in the texture of the very high resolution airborne photos that the model can learn with some kind of activation to produce biomass at plot level. And this is very promising because if we can get access to the plot data with their accurate geolocation, we have a lot of high resolution images, and we could make basically a national forest inventory with a very, very high accuracy, much higher than everything that exists so far. So in the end, I don't need to convince you that we need an integrated forest monitoring system, that artificial intelligence is very exciting. We have big data from satellite, but we are still in a world where the product you can derive from satellite and AI are still as good as the quality of the ground-based data you have to evaluate them. So we are still very much dependent on the availability and on the quality of the ground-based measurement. Maybe in 1 decade, the AI will do the job of forest inventories, and we don't need forest inventories anymore. But we are still on the fringe of relying very much on accurate ground data. So conclusions, there is a deluge of satellite data from different sensors that no research group, no postdoc, no brain can make sense of. Previous physically based retrieval models, because you have different wavelengths, different observation system, it's more and more difficult to use physical retrieval models to achieve a fusion of this data. This is the reason why some people have taken advantage of deep learning to try to move deep learning models into forest monitoring systems. We think that tree-level data is made possible now using very high-resolution imager or airborne data. As I said, ground-based data remain critical for the evaluation of satellite product. And I want to say, it's not a call for arms, but that if you have plot data, since we now have all this annual change of height, we see the degradation, we see the growth, we would be very interested to analyze the mortality and recovery with your help to try to understand better the carbon balance of forest. So thank you very much for your attention. I hope I was not too long.
Philippe, thank you so much. I think I speak for us all that this was quite impressive, and really the density and the amount of work that you've been doing on this is really just amazing. So really, really impressive. There have been a number of questions coming in, and I will try to digest and relate them to you with the help of my colleagues from the Tree Mortality Network here. The first group of questions sort of clustered around the use of JEDI, and particularly the limitation of JEDI in the high northern and southern latitudes. So when you do your global mapping and your global products using JEDI, how do you deal with this limitation? And this came both from Rico Fischer and Eric Willen.
It's a good point. I was a bit quick. Is that JEDI has no data north of south of 52 degrees. So we just train a model where we have JEDI data, and because we have Sentinel data everywhere, we can produce a global map in Canada and Russia. But how good it is when we basically got out of the model training for application, it is something we need to find out. So we are now trying to evaluate the JEDI-based map in regions where there is JEDI data and outside regions where there is JEDI data against a large data set of ALS data from our colleagues from Bristol in order to have a better idea of the performance of the model. If the performance is a disaster in the high latitudes, we can still use ISAT2. And that's what we would like to do, is we would like to combine both JEDI and ISAT2, which is a photon counting instrument in the generation of the maps where we have no JEDI data.
Wonderful. Thank you so much. I guess, well, there's a lot of questions. I'll try to get to all of them, or at least most of them. One that comes from Tom, and maybe Tom, you can jump in if I'm not relaying it correctly. I mean, what we're essentially doing is mapping states, but of course, from the idea of force dynamics, the underlying fluxes, so growth and mortality are the interesting constituent drivers. And then, looking at satellite data, particularly in dense forests, do you think that we can eventually get to disentangling these fluxes that make up the signal that we're seeing?
Well, depends on the flux. If it's a huge stand replacing disturbance, we will see a very clear height loss. If it's a cryptic mortality event affecting only the understory tree, it will be much more difficult. We see degradation features in the Amazon. We have this annual map at 10 meters for 5 years. And when we look at degradation features in Mato Grosso, like selective logging or things like that, or ground fire, we see a drop of height. So this is detectable. I guess if we want to do better, we can use the planet data. There was a nice paper by Ricardo Dalagnol over the Mato Grosso, where they used the planet mosaic at 5 meters, the NICFI data, and they were able to detect and to classify all the degradation features, at least for the anthropogenic degradation ones. We can also exploit the JEDI waveform, because in everything that I showed, we were going for the low-hanging fruit to predict the maximum height. If we try to use deep learning to predict like RH40, it doesn't work very well, because the Sentinel are seeing the top of the canopy and the JEDI is measuring the depth of the canopy. So what we are trying to do now is to build not deep learning, but it's called contrastive learning. You can try to look at the similarity between the texture of the Sentinel data and the complete shape of the JEDI waveform. So instead of trying to regress height at each level, you try to make some similarity or dissimilarity classification between the waveform of JEDI and the Sentinel images. I don't know if it's working yet, but if it works, it's very promising, because we can then model the entire waveform of JEDI, which is much richer in terms of information on the canopy depth to infer the biomass and the biomass changes than just the top height.
Wonderful. I mean, this will basically allow you to go at structural changes as well. I mean, if you have the top canopy dying, but sort of a second layer persisting in the disturbance, or the other way around.
Exactly. We would love to be able to accurately reproduce the JEDI waveforms, but I don't know yet. It seems to be promising, but I don't know yet if we're able to do it as well as for the top height.
I have a related question to that one. You said it depends on the type of the disturbance. One thing that we struggled with, that we encounter quite a lot in the European context, is that a lot of the disturbed areas are salvage logged. So basically, you have a disturbance, and then the managers come in and they put another human disturbance basically on top of it. And that makes it sometimes really hard to disentangle what's human, what's natural, what type of natural disturbance was the trigger in the first place. How do you address this in your work in France or Europe, or maybe even
we are facing the same problem. It's also a big political problem, because if you say your harvested area increases, okay, it's because you take more wood than needed. But if you say, okay, I need to increase the harvest because there is bark beetles and this salvage logging, it's a very different political story. So the forest industry is saying it's not us, it's the bark beetles. And the way we can find out to, let's say, deconvolute this is that if we have sentinel data every 5 days, we can see some precursors of disturbance, like beetle signal is relatively easy to detect, which is the near infrared band. And then we will see eventually that the forest has been marked to cut, and it is cut. Because in France, they mark the forest to cut, like the trees are damaged, but they only have the resources and the manpower to cut it maybe 2 years after. So they don't cut like firemen, immediately after there is a bark beetle detection. They cut when they go to the place and they know that this place has to be cut. So by looking at the high temporal frequency, I hope that we will be able to see this cascading effect of disturbances, but it's quite challenging. Huh? For instance, I was in the field and I learned that I thought that when the beetles attack, the trees become red and brown. But in fact, if the beetles attack in the fall, they stay green, and it's only when the sap wants to go up in the next spring that the next spring they become red and brown. So the spruce trees can still look green and healthy if the beetles have attacked them in autumn, but they only start to show sign of being killed a few months later. So I start to realize the complexity of this disturbance thing that you guys know very well. And we need to be quite careful in this kind of temporal detection signal. Huh?
Yeah, wonderful. Thank you. I mean, we're basically out of time, but I think there's so much more questions that I would take some more of those and go a little bit over time, if that is okay with everybody. There's a number of technical questions, and I'd start with one that I'm also interested in from Power Arellano, who asks about more specifics on the machine learning models that you use. So which type of machine learning, and probably also which types of frameworks you guys are using in the work that you're doing?
Well, as I said, we use UNet model. So UNet takes an image, it makes a series of convolution to reach some kind of latent images, and then it goes back to reassemble the latent images to match the data with the loss function. And then, of course, it adjusts the weight of the convolution, which are like the coefficient of linear regression if you had a linear problem. UNet is nice and flexible, but we have been finding better performances with the vision transformer model. There was a group from Meta, from Facebook, who also used vision transformer with very high resolution radar data. In the tropical forest, vision transformers have less of a problem in the underestimation of tall trees. But UNet seems to be quite satisfactory, although I'm not an expert of all this. And then this contrastive learning, basically contrastive learning is methods used for facial recognition to recognize cats and dogs. If I ask you to distinguish a cat and a dog, if you look only at the details, like the shape of the ears, unfortunately, some dogs have, sharp ears, like cats. So you cannot just look at details, but you can transform the image into something that looks similar, like the shape of the nose and the ears, and then you can associate things as being similar or dissimilar. And that's what we try to do to basically classify the Jedi waveform as a function of the sentinel properties. So we use UNet. We are happy with UNet, but there are better models. It's always a trade-off between computing power and performance without overfitting.
Wonderful. Another more technical one, but it's also interesting, is from Martin Turner, and he asks, how do you separate the influence of the influence of moisture from the biomass signal in the VOD?
Yeah. We have been killed by reviewers since we started to publish on VOD because he's right. VOD, in a sense, it's a water content. So we can try to do some statistical models to use water proxies like LSWI to try to get a part which is biomass and a part which is water content. The other thing we did is that we take the difference of VOD from the wet season to the wet season. Like you are in the Amazon and you think that during the wet season, there is so much moisture that the trees have reset completely their water content. So if you make the difference between a wet season and a wet season, you have something which is close to a delta biomass rather than delta water content. So my question to you guys is that, okay, it works for the Amazon because there is always a very wet season, but is there some regions where during 1 year, the trees do not restore their complete water content. So they shrink, and then it's only 1 year later then they get back to their maximum water content. If this is the case, of course, then the VOD would be affected by some problem. If there is interannual changes in water content, because we don't use a seasonal signal, we use the interannual change. The other problem with VOD is that when you have a disturbance, like bark beetles or fires, what is the water content of the dead trees? I found one paper from Canada, and I thought that the dead trees, they are black, they are dead, they are not moist. In fact, they have 37% of moisture. So dead trees keep the moisture. There is no sap, but they keep the moisture. So all the radar measurements should also be sensitive to the biomass or the moisture contained in the biomass of dead trees. So it's very difficult using, I think, radar or VOD data to separate the biomass which is dead from the biomass which is alive, because they both contain water. And honestly, I don't have enough knowledge on this, but this can be an issue.
Wonderful, thank you, Philippe. I think there's two more things that I want to pick out, and apologies to all the participants whose questions we couldn't address, because I mean there's so much great stuff there that Philippe presented, and I'm sure there's so much questions we could continue this for long. But there's two more things, and I think one that is interesting for a large majority of people, and Emilio Vignano asked this. Is the height map publicly available? And I think the question that is more broadly, I mean, you know, the stuff that you've presented, I mean, is this available for the community to use?
The height map for France is available on the Zenodo. The global one, we need to evaluate it against the ALS, and as soon as it's published in the data paper, it's globally freely available. The Planet data from Martin Brown Group, it's more of a problem because Planet is a private company. And basically, they forbid you to sell the derivative of the third derivative of their product. So the map of Martin Brandt are available on request for research, which doesn't mean that he's defensive, that you send him an email, you get the map. But Planet is careful that he doesn't give the map for any commercial application, because the agreement is signed with Planet to have a cheap price. Basically prevents him from making the map freely available on the Zenodo repository. Otherwise, all the data from Martin Brandt's group paper are really freely available on request. And it's not a trick to not to give the data, like sometimes it's they are really freely available.
And the last one is more of a comment, but I think it's an important one also because you've stressed the value of inventory, and it's from Gilberto Freitas from the Brazilian NFI. Who basically says that with the approaches that you presented, what we can basically do is reduce a little bit our densities in the NFI, but focus also some of the field work on aspects that probably remain still hard to measure from remote sensing, and basically develop a different type of inventory that's informed, or there's a feedback between the remotely sensed monitoring and the inventory that we do on the field, on the ground. And I think this is well, at least, you know, personally, as somebody also that I will be out in the field tomorrow looking at some of our field plots in the snow. This is something that I find quite interesting and relevant. And so I'd be interested also to hear your thoughts, probably as a concluding remark on this relationship between, you know, what we can do with remote sensing and artificial intelligence, but then also how the boots on the ground work fits into all of this.
Well, I think, of course, the remote sensing has such a good coverage that when the data of good enough quality, they provide the better budget, it's clear. But on the other hand, it's easy to produce a very accurate height map. But if I show you the accuracy of my biomass map, the correlation is 0.2, and the height map is 0.7. So the allometry in a forest between top height and biomass is dramatic. So if you don't have forest inventories with a different structure of forest to have a very good conversion of height to biomass, you're not going to do biomass just from remote sensing. So I would argue that we can do height very easily, and now I believe accurately. But to go from height to biomass, especially in tropical systems, you need absolutely the inventory plot, because there are so many combinations that nature can find between height and biomass, that the same height can have completely different biomass. That, in my opinion, is super important to keep and even to reinforce the field measurements.
Wonderful.
One
I think
problem
this,
also is the density of the wood, because even when you have a very good volume, okay, you have a perfect inventory with the TLS and so on, you are very happy, you shake hands with the satellite guys, you have solved the problem, and still you have wood density that vary between 0.4 and 0.9. So then you are still stuck to do the biomass.
wonderful. And just opened up another dimension. I think that's the beauty of science, right? I mean, we're not running out of questions anytime soon, regardless of the big leaps that we are making, and particularly, Philippe, you and your group have been making. Thank you so much for making the time. I'm well aware that your presentation schedule, you're very well in demand and your schedule is quite dense. Thanks for making time for this. I think this was a wonderful seminar. Thanks everybody for tuning in. And I'm looking forward to seeing you at the next seminar, and stay tuned for more. Goodbye.
Bye-bye.